Hello. Just want to make a video about 12.2 that we covered today. In 12.2, we started looking at vectors and what they really are. And I've got this picture right here, and it just looks like a stick with an arrow on the end. You could even think of a pen as being a vector. But the most important things about them are these labels that we have here. So number one is the tail. The tail is where a vector starts. And then we have the head of a vector, which is where the vector ends. Every vector will point in some direction in space. If it's 2D space, then it'll just have X and Y values that give it direction. If it's 3D space, then it will have X, Y, and Z values that give it direction. The last thing on here is the magnitude, and the magnitude is just another word for length. We always have length being a positive thing, so you'll never have a negative length on the value of the magnitude. And let's go into notation now. We'll get to like how we work with vectors and what we can do with them in a little bit. So the notation for a vector, oftentimes in textbooks, you're going to see a bold-faced letter. Like, for example, you might see something like this V. But I had to really stress to write that to look like a boldface. So that's not how we typically write vectors if we're using handwriting. So this is bold-faced. And we would see this in textbooks. But what we're going to use for handwritten vectors, we are always going to have some other symbol that lets us know we're working with a vector. So two of the more common ways to write a vector, these are both totally acceptable. One is to have a V with an arrow over the top of it. It's kind of a half arrow because it doesn't have, it only has one side of the point on it. But this is, universal notation for a vector. Everybody knows it's a vector. There's no question in anyone's mind that this would be a point. This is a vector. Another one that you could use is a V with a caret symbol over the top. And everybody knows that that's also a vector. So you're going to see these two different types of notation in mathematics versus physics or engineering. So just kind of be on the lookout that there are different ways to represent the same thing. Now, speaking of different ways, we have a different way to write our notation for a point versus a vector. So for a point, if we wanted to represent some point in space, we might give it a name, P, but then we would use parentheses, and I'm going to use the numbers 2 and 3, for example. So this would tell me, oh, the point 2, 3 in 2D space. But a vector looks a little bit different. It's subtle, but it is important. It has angle brackets. And so we'd have an angle bracket and then the 2, 3. A point is one particular spot in space. A vector is like a pointy stick, okay? So make sure that when you're using your different notations, you are using angle brackets for a vector and you're using your parentheses only for points or for intervals possibly. All right, a directed line segment. So, I've got all the words up here on what a directed line segment is, but I've also got a great picture here. So this particular line here in space that starts at the point C, which is represented by x1, x2, and it ends at the point D, which is represented by x2, y2, this is a directed line segment. It is called that because it points in a direction, and it is a segment. It's not infinitely traveling in both directions. It starts at C, it ends at D. That's it. It's a segment. But this is actually totally the same thing as AB. So we're going to call this directed line segment CD. I'm going to put a little hat over the top of it, and that represents that it is also known as a vector. This guy over here that starts at A, which is represented by the origin, and ends at B, which is represented by AB, this is a position vector. And it is called AB. Now, CD and AB, believe it or not, are the exact same thing. Notice that they are pointing in the same direction and they have the same length. Might not be totally obvious that they have the same length, but I promise you they have the same length. So we have this concept here that CD is equal to AB. They might be in a different position in space, but they are not pointing in different directions and they are not different lengths. And so that's kind of an interesting feature about vectors. They can be represented by directed line segments in space, or they can be represented by position vectors where the tail of them always starts at the origin. For our purposes in this class, we will primarily be working with position vectors. So we've got to figure out how to come up with a position vector when we've been given a directed line segment. So for example, the directed line segment CD, if I want to get that into vector notation, the way I do that is I have to find out like what is its length with respect to x and what is its length with respect to y. I'm not asking about magnitudes here. I'm asking about the idea that it's kind of slanted. And so there's a change in x values and there's a change in y values. And what are those? Well, since we've been given generic points, the change in x values is just x2 minus x1. And the change in y values is just y2 minus y1. This vocabulary I'm using may be very reminiscent of the idea of the slope, right? So change in y over change in x gives you your slope of a line. It also gives you your slope of a vector. Now, these changes are in fact equivalent to coming up with the values a and b in a vector form, which is the endpoint of the AB position vector. Okay, so what you're going to do, you're given 2 points. You're going to take the x values, take the one that's furthest to the right, and subtract the one that's more to the left to get your x component. So these are going to be the x component and y component of the vector. And then for the y values, we do the same. We take the rightmost y value or the uppermost y value that goes with the rightmost x value and then subtract the leftmost one. So let's see how we do that. We have this example, pardon the hand-drawn graph. In this example, we're asked, does u equal v? Does the vector u equal the vector v? So if I try to define for myself what u is, it looks like it's made up of a directed line segment with points A and B. So I'm going to go ahead and make AB into a position vector by taking the rightmost x value, which in this case comes from the point B, and that is 2. I'm going to subtract the leftmost x value, which is -1. That's coming from my A. And then I'll go to my y component, and I'm going to take the 7 that's in the B point and subtract the 3 from the A point. And this is going to leave me a vector with components of 3 and 4. All right, so if I want to know if this is the same as the V vector, then I need to create my V position vector. So V is going to be coming from the directed line segment CD, and now we're going to make it into a position vector. We take the rightmost point, that's the D, and so its x value is 5. We subtract the 2 from the point C. Then we go to our y component, we look at 9 minus 5, and that's going to give us a final position vector that has components 3, 4. And we can say, yay, they're equal. So the answer to the question is yes. That's it. If you're asked if something is something or it's not something, your answer is yes or no. And in this case, we've done the background work to determine the answer, and it is yes, they do equal each other. So then what we need to do is recognize that when we came up with the vectors 3, 4, those are the position vectors of both of these directed line segments. And so we could draw that. And so we'd start at the origin and then go over 3 units in the x direction and up 4 units in the y direction. And then we would draw a vector from the origin to that final position. And this, I'm going to call it u, since u is equal to v. I can use either one to notate that vector. But that is my position vector. So in the next question where it says, what is the position vector for the vectors in example 1? It is u, well, which is also equal to v, which is 3, 4. Okay. The next question is asking about the angle that the position vector makes with the positive x-axis. So we're looking for this angle right here that we would get when we look at our graph. What we have to remember is a couple of things. Number one, that tangent of theta is equal to y over x, and we get that from trigonometry. The next thing to remember or to notice is that when I drew this position vector, I made a point of showing that I went 3 units to the right and I went 4 units up in order to come up with where my position vector was pointing to. And so what that equates to is a y value and an x value. And so then I can very easily say that theta is equal to the arctangent of the y component of my vector divided by the x component of my vector, which is 3. So theta's arctan of 4/3. That doesn't give us a pretty value, so we just call that an exact answer and don't worry about an approximation for now. But if you wanted to, you could always plug this into your calculator to get an approximate value. For now, we know this is an exact value. And one thing I can say is it is a value that is less than 90 degrees because it is in the first quadrant. So at the very least, I know that. All right, next thing is magnitude of a vector. So right at the very beginning, when I showed you the picture of a vector all the way up here, I talked about magnitude being length. So in the last class, we did a bit of a review on how to calculate distance, and we saw how distance is related to the equation of a sphere. What we're going to see here is that distance is also related to magnitude because distance and length are the exact same thing. Now, we have some notation that's a little bit different right here. We have these bars around our V. They look like absolute value bars. And in fact, they are, but they're used in just a different frame. Absolute value bars, when we have the absolute value of a number, what we're actually defining is the absolute distance from 0, which is length, right? So absolute values were always giving us lengths to begin with. So to use the absolute value bars in the case of the magnitude, which is length, it's not a far stretch, okay? So inside here, this is distance. And what we've got here, we've got a v vector. V has components v1, v2, and v3. And so the magnitude of v is by definition going to be the square root of the sum of the squares of the components from the vector. Now notice that if v1 is equal to x2 minus x1, and v2 is equal to y2 minus y1, and v3 is equal to z2 minus z1, then the magnitude of v is equal to, I'm going to need more space there. Hang on one second. This is why I can never go back to paper. So then my magnitude is going to be the magnitude of v equals the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, which is exactly our distance formula that we were using in 12.1. So hopefully just seeing that tie in how, yes, we have new notation, but really we're not using anything new. Hopefully that's helpful in how you remember how to calculate a magnitude. Okay, so example 2 says find the magnitude of the position vector that was representative of the vectors from example 1. So I just have to scroll up a little bit. My position vector was 3, 4. And so I'm going to go ahead and say the magnitude of u, which is also the magnitude of v, is equal to the square root of the sum of the squares of the components. So it's 3 squared plus 4 squared, which gives me 9 plus 16. Or in other words, it's the square root of 25, and that is 5. And that kind of makes sense. If you think back to right triangle trigonometry, we learned about the 3, 4, 5 triangle, right? So we have a 3 and a 4. That means your hypotenuse has to be 5. So, just try to tie together what you know from trigonometry when you're working with these vectors and angles and lengths and whatnot. Okay, back to the notes. The zero vector. So the zero vector, believe it or not, needs to exist. We can't just have the zero number. We have to have the zero vector, because a vector will have components. And the interesting thing about the zero vector is that it has zero magnitude. If you were to square 0 squared plus 0 squared plus 0 squared, you get 0, and the square root of 0 is 0. So we have no magnitude on a zero vector. And because all the components are zeros, there's also no direction either. The zero vector is merely a point, but it's a point at the origin, and we need it to exist for certain situations, just the idea, the concept of taking a vector and then subtracting itself from it. For example, we could have the vector 1, 2, 3, and we subtract the vector 1, 2, 3. Without going into the details of how to add and subtract vectors, we can see that we have a thing and we're taking away the same thing, which should leave behind 0, right? But it can't just be a number, because if you take a vector and then you take away a vector, you should still have a vector solution. You need placeholders. So it's not just 0. It's going to be the vector with components 0, 0, 0. All right. The next thing is a unit vector. So this word unit, very important. What it's telling us is 1. The magnitude of the vector is 1. And so right away we can say a unit vector has a magnitude of 1. But then we need to know, how do you make a unit vector? So I like to think of the idea of just plain old numbers, right? If I give you or even just lengths, if I tell you the length of a stick is 9 inches, and I really just want a unit stick, then dividing by the length of the stick, so that would be 9 divided by 9, well, that would give me a 1-inch stick. That would be a unit stick. So I want to use that same concept when it comes to making a vector, any old vector, into a unit vector, because it's exactly what happens. We just divide out the length, and then we have what we want. So in order for this vector A that has components 2, -3, and 7 to be made into a unit vector, here's what we do. So the unit vector is u. So we usually use u for unit vectors. We also use u in other cases, but if we're talking about unit vectors, we always call them u's. And what it's equal to is the original vector A over the magnitude of the original vector A. So we can plop those things in there. We'll plop in A. It's got the vector 2, -3, and 7. In the denominator, by definition, the magnitude of A is the square root of the sum of squares of the components. So 4 plus 9 plus 49. That adds up to root 62. So there are a number of ways I can represent this. A lot of you will probably write it this way to begin with. 2, -3, 7 all over the square root of 62. You could also write this as 2 over square root 62, negative 3 over square root 62, and 7 over square root 62. I personally like to write it with 1 over the square root of 62 on the outside, because I don't want to write over square root of 62 3 times, although I just did it. So I keep that 1 over root 62, pull it out to the outside, so it's just a multiplier. And I leave behind the 2, negative 3, 7. So what I've kind of done here is showed you a little about what it means to have a constant multiplied by a vector. Or if you have the same constant in each of the components of a vector, you can factor it out to the outside and write it as a constant multiplier. And we'll talk in a moment about what that is called. Before we get there, we need to talk about the standard basis vectors. So what those are is they're unit vectors. They run parallel to each of the axes of the plane or the octant. So, focusing on the 3D case, there are often situations where we would like a vector that represents one of the standard axes, x, y, or z, but has only a length of unit 1, okay? And so we decided, or somebody decided, that we would call these I, j, and k. I, right here, that is always the unit vector that runs along the x-axis. J is always the one that runs along the y-axis, and k is always the one that runs along the z-axis. And so we could just write what these are so that they are on our picture, so that I hat is the vector 1, 0, 0, j hat is the vector 0, 1, 0, and k hat is the vector 0, 0, 1. Okay. Now, because we can write a standard basis vector in this angle bracket notation, that means that we have a way to go back and forth between two different types of notation. So this guy right here, A is equal to the vector A1, A2, A3 in the angle brackets. This is called the component form of a vector. And now we can play with it a little bit. And so I am making a bit of a reach here in this explanation because we haven't talked really about the addition of vectors. So just trust me for a moment that we can do this. We could take a vector with A1, A2, and A3 as components and rewrite it as a sum of 3 vectors, where each one of the vectors gets 1 non-zero component and 2 zero components. So like this first one, A1 gets to be in the x position, and then we have 0, 0. The second one right here, A2 is in the y component, and then there's a 0 and a 0 for x and z. And same here with the last one, A3 represents the z component, and there are zeros elsewhere. This idea of being able to factor a number out, we could factor the A1 out of the first vector and leave behind this 1, 0, 0. Factor an A2 out of the second vector and leave behind a 0, 1, 0. And factor out the A3 from the third one and leave a 0, 0, 1. But then notice the vector 1, 0, 0, that is just the I hat. That's the standard basis vector along the x-axis. 0, 1, 0 is j hat. 0, 0, 1 is k hat. So now I have another way to represent a vector. I don't have to use component form. I could use what is called the standard basis vector form. You get to decide. I personally use the vector or the component form of a vector just about always, mainly because I'm usually typing my vectors, and so it's easier for me to do angle brackets than it is to give i's, j's, and k's little hats over them. But you decide. In WebAssign, we had a discussion in class as to whether we can use the greater than and less than in order to indicate our angle brackets. So you want to try that out. Let me know if that works. But otherwise, in the math palette, there is an option for angle brackets in there. The I's, J's, and K's are also in the math palette as well. Okay, so quick example, just like how to go back and forth. It might seem simple for some of you or trivial, but this is something that people do make mistakes on, so I don't think it is necessarily trivial. If I want to write the component form of a vector, 3, negative 7, 2, in a standard basis vector form, what I have to do is drop those angle brackets and get rid of those commas, put some I's, J's, and K's in, and add everything. So here's what that looks like. 3 I hat minus 7 J hat plus 2 K hat. That's it. It's no more than that, okay? And then we want to look at vice versa. If I have a standard basis vector form where I have 5 I hat minus 3 J hat plus 2 K hat, and I want to rewrite that in component form, then I have to get rid of the I, J, and K, get rid of the sums in the middle, and get some commas in there. Now, notice I said get rid of the sums. Don't get rid of the subtraction, just turn it into a minus sign. So the component form here is going to be angle bracket 5, comma, negative 3, comma, 2. Okay, so just make sure you're comfortable going back and forth, and you can decide which form you like to use best. I'm not going to tell you to use one or the other. Okay, just pick one and get comfortable with it. All right, now that we know what vectors are, we know how to make a unit vector, we know that there's a zero vector, we know the two different ways to write them, we've got to talk about our operations. And I have to apologize, I did neglect to put something in between the addition and the multiplication, so I'm going to have to scroll a little bit to get there. All right, so when we look at these pictures here, we're looking at a parallelogram and we're looking at a triangle. On the left is a little parallelogram that gives us a law. And what it is saying, okay, because this is like a geometric interpretation of what it means to add two vectors. So if I want to find A plus B, I would start at the tail of A, and that would be placed at the origin. Okay. Then normally the B vector would also be placed at the origin, but if I'm adding two vectors, I need to pick up my B vector and put its tail on the head of A. I should change that color. There we go. And then don't let B change its direction or its length. Just let it, lay as it is. And the head of B will be the point that A plus B points to. Okay, so A plus B is basically, it looks almost like the legs of a triangle or two sides of a triangle. And then the A plus B, that vector is like the hypotenuse if this ended up being a right triangle. Otherwise, it's just another of the legs. But what the parallelogram law is showing here is that whether we take A and then add B, or we take B and then add A, we get the same thing. We end up in the same spot. So what it's saying is that we can add in any direction. That means A plus B is equal to B plus A. But by looking at both of them, A plus B and B plus A, we form the four sides of a parallelogram. And later on, we'll see what other sorts of great features we can get between vectors and parallelograms. But ultimately, we form a parallelogram, which means that vectors are parts of a parallelogram. The triangle law. Now, the triangle law is, let's see, let me just real quick. The triangle law is just the resultant vector, so it's not focused on this commutativity of addition. The triangle law shows you visually the resultant vector when adding vectors. Okay, the sum starts at the tail of the first vector and ends at the head of the last vector. And I'm not saying the second vector because you could add, more than two vectors together. So you would, geometrically, you could line them up all head to tail, head to tail, head to tail. And when you get to the final tail, now connect the tail of, when you get to the final head, connect the tail of A, your first vector, to the head of the last vector. And that position vector right there will be the total sum, or in other words, your resultant vector. All right, now algebraically, this is where I have to scroll a little bit. I should have placed this elsewhere. So what we've got here is addition and subtraction all together in our definition of addition and subtraction. So whether we're adding or subtracting two vectors or three vectors or four vectors, doesn't matter. What we do is we write out our vectors, say it's A plus or minus B. We're going to write out A with its components plus or minus B with its components. And what we do to combine them, to actually perform that addition or subtraction, is we take the first components, those are always our x components, and we add them or subtract them. Then we take our second components, the y components, and we add them or subtract them. Then we take the z components, the a3 and the b3, and we add them or subtract them. That result is our resultant vector. Okay, now I'm going to move back in time and go to my multiplication. So there really are three different types of multiplication, but in this section we will only cover one, and that is scalar multiplication. But this word scalar is kind of weird. All it means is constant. So like a number, 2, 1/2, a third, 3.7. Those are all numbers. When we do scalar multiplication, what we are doing is we're taking a number and we're scaling all the components that are inside of a vector. So for example, if we look at this geometrically, if this first vector right here is u, then if we were to multiply u by a 2, the 2 would double the entire length of the vector. But the only way it could do that is if the 2 was multiplied into all of the components. So if this was u1, u2, u3, then 2u would be 2u1, 2u2, and 2u3, right? So you could distribute that number all the way through. And if we are halving our vector, then it would shrink by half, and all of the components inside would also get shrunk by half. So this one right here would be 1/2 u1, 1/2 u2, and 1/2 u3. The last one, a -1 times a u, what this does is it takes your vector and flips it 180 degrees. So if we were to write this in component form, it would be minus u1, minus u2, and minus u3. Okay? So algebraically, I've already kind of shown it up above, but algebraically, if we have a number times A, our vector, I don't care what the number is. It can be rational, irrational, positive, negative, doesn't matter. You can take that number and you can distribute it to all of the components inside of your vector, and they all get scaled. Ergo, the name scalar. The second and third multiplications won't be covered till 12.3 and 12.4. 12.3 is the dot product. and then 12.4 is the cross product. And I guess what's interesting about that is, with regular old numbers, when we learn arithmetic, there's one type of multiplication. That's it. But with vectors, there's 3 different types of multiplication that are defined, and they all give us something different. So we do need to really pay attention to what kind of multiplication is happening. All right. But we're going to keep going with what we have. Let's say that we have 2 vectors, A and B. A has components 2, -3, and 7. B has components -1, 4, and 5. And we're told to calculate -2 times A plus 3 times B. Well, -2 and 3 are just scalars. That's it. So we should be able to do this. I'm going to take a -2 times A plus 3 times B. Now I'm going to go ahead and put in my A vector. So it's -2 times the vector 2, -3, 7, plus 3 times the vector -1, 4, 5. Now I'm going to distribute those scalars through. When I distribute a -2, all my signs will change as well. So I get a -4, a +6, and a -14, plus I'm going to distribute the 3. I get a -3, a 12, and a 15 in my vector. Now I can add the like components. So this gives me -4 minus 3 in my x component, 6 plus 12 in my y component, -14 plus 15 in my z component. And then I go ahead and finish my addition. -7, 18, and +1. Those are the components of my resultant vector. Okay? All right, subtraction. We just want to see really what this is geometrically mostly, because subtraction is really the same thing as adding a -1 times something. So it's not a huge leap from addition. So in this first picture here, I have 2 vectors, u and v. Here's my u vector, here's my v vector. And the first picture is showing the addition of u and v. So u is in its position vector form. V has its tail sitting at the head of u. And then the resultant vector u plus v is this red dashed line. Now look closely at v and the way that it is positioned. Its direction is up and slightly to the left. And so if it was in a position vector form, it would be, let's see if I can get this on here, it would be approximately something like this. Okay, that's V in the position vector form. So we just had to move it over, but because we were adding. But what if we were subtracting? Well, the subtraction, what I would do for geometry's sake is I would first multiply it by a -1. And that would then put it down here. So this is -v. Now go to the second picture. My -v now, it has its tail sitting at the head of A, and it's pointing down, and it's parallel to what kind of, my drawings aren't very good, but it's kind of parallel to the -v vector that I drew in the first graph. And so then my resultant vector, u minus v, is in a completely different place than u plus v was. But really, it's still the same process. We just have to first flip the second vector, and then we can go through the process of addition, lining up the heads to tails. All right, and we already did the algebraic process. Okay, one more quick little exercise. We're given the same vectors, A and B. A is 2, -3, 7. B is -1, 4, 5. We are asked to calculate the magnitude of A minus B. So the magnitude of A minus B, inside of the magnitude bars, I'm going to go ahead and write my A and my B. So I have the magnitude of 2, -3, 7, minus the vector -1, 4, 5. Then I'm going to go ahead and combine my like components. This is equal to the magnitude of 2 minus a -1, -3 minus 4, 7 minus 5. That takes care of my subtraction. I need to just combine those now. So I still have the magnitude, and my vector, the difference vector, is now going to be 3, -7, and 2. All right. Now I can take the magnitude. Remember, the magnitude by definition is going to be the square root of the sum of squares of the components. So 3 squared plus -7 squared plus 2 squared. This gives me 9 plus 49 plus 4 for a final value, the square root of 62. All right. Now we want to look at applications of vector addition or subtraction. Because it's all fine and dandy to learn what these are and how to do things, but where are we going to ever use this? One application of adding vectors is to come up with the resultant force on an object when you're given all the vector forces that are acting upon that object. And the resultant force is then just going to be the sum of the individual forces. We're going to go through an example that deals with that. But this next little blurb talks about, sometimes we're given a situation where all we know is the magnitude of the vector and the angle that the vector makes with the positive x-axis. And if you don't know this next little equation right here, you don't even know what to do. But it turns out if you need to come up with the components of a vector, and you only know the magnitude and then the angle, you can come up with the components of the vector. So for example, our vector is v, and its components, the x component is the magnitude of v times the cosine of the angle. Its y component is the magnitude of v times sine of the angle. And this is all just coming from right triangle trigonometry. If I have some vector, the magnitude, remember, is the length of the hypotenuse of a triangle that gets formed when we look at the change in x and the change in y. Theta is this angle that's made between the positive x-axis and our vector. And if we want to know, for example, the x value, then we could say that, cosine of theta is going to equal the adjacent side over the hypotenuse, and our hypotenuse is the magnitude of v. So then I could solve for the x component, and it's the magnitude of v times the cosine of the angle. So that's how we're coming up with those. And we could do a similar scenario for the y value. Sine of theta is equal to y over the hypotenuse, which is the magnitude of v. And again, we could solve for y. Y is going to be the magnitude of v times the sine of the angle. So it's not arbitrary where these are coming from. It is coming directly from right triangle trigonometry. Let's see how we can use that. All right, in this next example, we're given a picture, first of all, and the picture shows two force vectors. And those force values that we're given are magnitudes of the vectors. We are also given some angles, and we're told to find the magnitude of the resultant force and the angle that it makes with the positive x-axis. Resultant force is the sum of the vectors. So we need to remember that that's all we're being asked for when we see this fancy little term here, resultant force. It's easy to get scared by that stuff. So the first things that we have to do is maybe give these two vectors a name. I'm going to call the vector that's in the first quadrant A, and the vector on the negative x-axis, that'll be B. So for A, we know a couple of things. We know that the magnitude of A is equal to 200 newtons. And we know that the angle made with the positive x-axis is 60 degrees. For B, we know it looks like it's 300 newtons. The magnitude of B is 300 newtons. And the angle that B makes with the positive x-axis is 180 degrees. All right, so now that we have that, we can start doing some calculations. First, before we can even think of the magnitude of the resultant force, we have to come up with the two vectors that are even going to be added to come up with a resultant. So we need our A vector. A, just following the formula up above for that V vector, it has components magnitude of A times cosine of theta, magnitude of A times sine of theta. Now I'll go ahead and pop those values in. This gives me 200 cosine of 60 degrees and 200 sine of 60 degrees. Cosine of 60 is 1/2. So we have 200 times 1/2. And sine of 60 is √3 over 2. And then we just simplify that one more step. This is going to give us the components of 100 and then 100 square root 3. That's A. B, we're going to use its magnitude, which is 300, and then cosine of the angle, which is 180 degrees, and then 300 sine of 180 degrees. Cosine of 180 degrees is a -1, so this is going to leave me with -300, and sine of 180 is 0, so the y component is 0. Okay, so that's first. We had to find A and B. Second, we need to find the resultant vector, which is A plus B. Now, we very nicely have all the components up there, so if we want to add A plus B, we're just going to add the x components. So it's going to be 100 plus a -300. And then the y components are 100 square root 3 plus 0. And of course that simplifies to give us -200 and then positive 100 square root 3. Now I kind of want to see if this actually makes sense if we were to look at this geometrically. A plus B. So A gets to stay as a position vector. B has to be picked up and it has to have its tail placed at the head of A, and then it still points in the same direction and has the same length. And it looks like the resultant would be where this blue dot is. So this is A plus B. It is in the second quadrant, and so it makes sense that my x component is negative and my y component is positive. So I feel like I'm doing the right thing here. It's always good to have a check on that. The next part, we found our resultant. What are we looking for here? We're supposed to find the magnitude of the resultant force. So third, find the magnitude of the resultant, which equals the magnitude of A plus B. We already found A plus B, so our magnitude is going to be the square root of the sum of squares. So -200 squared plus 100 root 3 all squared. And this is going to give us, after we square and add, this is going to give us 70,000. That's an exact value. We could simplify it, but usually these problems are asking you to approximate, and they'll say like to the 100th place or something like that. So to the 100th place, this is approximately 264.58 newtons. And of course you want to ask yourself, does that make sense, right? So B was 300 newtons, but it had a negative x component. A was 200 newtons and it had a positive x and a positive y. So it kind of makes sense that our resultant force, the magnitude of the resultant force, would have a value somewhere between the values of A and B. All right, so that answers the first part. The next part is to find the angle that this makes with the positive x-axis. Well, that's not too bad because we have our x component and our y component for the resultant vector. So fourth is to find the theta that AB or A plus B makes with the positive x-axis. Well, remember, theta is equal to the arctan of y over x. So I'm going to plop in those y and x values from my components of A plus B. That's going to give me arctan of 100 root 3 over negative 200, which simplifies to give me arctan of negative root 3 over 2. Now, when I plug this into my calculator, I get an angle of negative 40.89 degrees. That is not in the second quadrant. That is in the fourth quadrant. And this is happening because arctan, in order for it to be defined, we have to put basically bounds on the domain of tangent. And so when we do that, we end up with, we define tangent so that it's between minus pi halves and positive pi halves, which means arctangent is always going to give us angles that are between minus pi halves and positive pi halves. So it makes sense that we got this. But in order to fix it so that we can be in the second quadrant, what we have to do is say, okay, well, that was bad. We don't like that. So this means that theta is in quadrant 2. So theta is equal to our angle, negative 40.89 plus 180 degrees, which is going to give us approximately 139.11 degrees. That is in quadrant 2. That makes me happy. I think it's right. Okay. So that's our process for some of these problems. That's a lot of work. And I realize it does take a while to work through these, but hopefully having these steps lined out for you, that will help you to work through the problems on your own in the homework. All right, next one. We are going to be looking at another example, but first we have these properties of vectors that we've kind of been using them, not necessarily naming them, but we do have these. The first property, A plus B is B plus A. That's our commutative rule. The zero vector, the second one, I should say, A plus a sum or A plus B plus a C. This is going to be the associative property. So you can associate in whatever order. 3, this is the idea of the zero vector. Like, how does it work? If you take a vector and you add a zero vector to it, you don't get anything. So this is kind of the identity, the additive identity, in the sense that it doesn't change things when you add to it. Going to number 4, A plus a negative A is going to equal 0. This is our additive inverse property. Additive inverse. In 5, we have C, the constant, times the sum of two vectors. This is a distribution property. In 6, we have basically another distribution property. In 7, we have an associative property. And so these are having to do with the scalar multipliers, the distribution and the associative. And then we have 1 times an A is equal to A. So the number 1 still acts like the scalar 1 still acts like an identity of it's not going to change something when you multiply by 1. Okay, now moving on to one more application example. Here we have a 100-pound weight. It hangs from 2 wires, as shown below. we want to find the tensions or the forces, T1 and T2, in the wires, and then the magnitudes of these tensions. So what I gave you guys in class as like a hint to start you off was you should draw a line underneath there and use some geometry to identify the angles that are on the other sides. So on the left-hand side, we have a vector T1, and T1 is like a wire that's hanging from an above parallel bar. And that T1 vector makes a 50-degree angle with that bar. And so by drawing a line parallel to the bar, but below the vectors, what I'm giving myself is a geometric property. If you have two parallel lines and you have a slanted line between them, the angles opposite each other are going to be equal. So those are both 50 degrees. Similarly with T2, I get that same property, so I get 32 degrees for my angles. Okay, when we are asked to find the tensions T1 and 2, we're asked to find vectors, T1 and T2. When we're asked to find the magnitudes of these, we're literally being asked to find the magnitudes. So that means we don't know a whole lot here. Okay, and somehow or another, we're going to still find things out. And what's going to help us is this 100-pound weight. Okay, so we want to kind of go back to the idea of how do you build a vector that has components when all you know is the magnitude and the angle that the vector makes with the axis. So I've got this 50 degrees thing going on here with T1. So I could write T1 as a vector with components. I'm going to leave a little bit of space and then write the magnitude of T1 times cosine of 50. So I'm using an angle 50 degrees that corresponds with the first quadrant when I have a tension that is pointing to the left and is clearly in the second quadrant. That means cosine of 50 would give me a positive value, but in order to end up in the second quadrant, I will need to put a negative in there. Alternatively, instead of doing this, I could make it a little bit more clear by saying, instead of calculating this, the positive angle that's made with T1 and the positive x-axis is 140 degrees, not 50 degrees. If I use that, I'll get my negative sign. It'll work into everything. So maybe that's less confusing. I don't know. The y value will be positive. So we're going to get our magnitude of T1 times sine of 140 degrees. Okay, the next thing to do is to go ahead and write out T2. So T2 is pointing to the right. It looks like we could represent it in the first quadrant. And in order to come up with the components, the x component is going to be the magnitude of T2 times cosine of 32 degrees. And then the magnitude of T2 times sine of 32 degrees. And then what we have is this weight, and I'm going to call it W. W has components, well, it's just pointing straight down, okay? Down is negative, and so it has no horizontal component, so that's 0, and the vertical component is negative 100. Okay, now, one thing that we kind of have to assume here is that if we were to add the T1 and T2